assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
29.44, do we have to consider quantum effects for sort of normal, everyday-sized rotating objects? And, your sort of intuitive answer is going to be no, but let's, be quantitative about this. So we want to find the differences, sort of the spacing of energy levels that you'd have for a rotating baton with some given masses and dimensions. So it's 32 centimeters long. There's a bar that has a mass of 230 grams, and on either end there are balls with masses of 380 grams. And it's spinning at 1.8 revolutions per second. So the kinetic energy is 1/2 I omega squared. And, the quantum number we can get, and it's going to be very large. So let's let its length be d just to sort of make our life a little bit easier while we're doing things symbolically. And so in that case, we're going to have the moment of inertia is going to be that for a rod, so 1/12 mass of the rod, d squared, and then 2 point masses, so that's just going to be m of the balls, and their distance from the center is 1/2 d, and then that gets squared. So now we can figure out what the quantum number is going to be. L times L plus 1 times h bar squared over 2I. And now, because L is very large, L plus 1 is not very different from L, so we can approximate this as just L squared h bar squared over 2I. And so we can solve this for L. It's going to be I omega over h bar squared, or no, over h bar, because we took a square root. And so then putting in all of our expressions for everything and converting 1.8 revolutions per second into radians per second, we get that L is an absolutely gigantic number, 2.30 times 10 to the 33rd. And so now we know what the spacing between rotational energy levels is. It's going to be delta E. And we can, as a sort of what fraction of the total rotational energy that is, we put that there. We know this is the rotational energy. So then this is going to be L h bar squared over I. And then divided by L squared h bar squared over 2I. We get this simplifies down to 2 over L. Remember, L is gigantic, 10 to the 33rd. And so we get that the energy level separation as a fraction of the total energy is going to be 8.7 times 10 to the negative 34th. Which is extremely small. And so the fact that the energy levels, the rotational energy levels, may be discretized because of quantum mechanics is sort of irrelevant here. And so we can say, based on a quantitative analysis now, that no, the quantum mechanical effects of macroscopic rotating objects are not relevant.